So the strength of intermolecular forces depends on the structure of the particles, and the state of the matter, solid, liquid, or gas at a particular temperature depends on the strength of the intermolecular forces. If we have strong forces, then we're going to need higher temperatures to melt the solid and to boil the liquid, because these strong forces are what hold the particles together. In some ways, intermolecular forces are like Velcro. And so if you imagine a bunch of people wearing Velcro suits and you're milling about in a small space, you're going to kind of stick to each other, right? And so it's going to be hard to move around. In order to move away from each other, you're going to have to use some energy, right? If you think about, where's my hands? You know, two things that are Velcro together and you have to rip them apart, right? If you have weak forces, you're going to have low melting and boiling points. Because what happens when something melts is we break some of the forces that are holding them together so that the particles can slide. When something boils, we're breaking those forces completely so that the particles can go into the gas state and be completely separate from each other. So the reason temperature is important here is because temperature is the kinetic energy, the motion of the particles. And so you can have a solid, imagine students sitting in their chairs, and at a low temperature, the students are all kind of lethargic and they're just sitting there. That's how it usually was at 8 a.m. Everybody's just kind of like dead in their chairs, right? If we gave everybody a sugary snack and a rock star, people might start getting a little bit jittery. Maybe somebody needs to use the restroom. We're getting kind of agitated and people are just kind of squirming, right, in their chairs. There's a lot more movement. That would be the solid state, but in a warmer environment, a hotter temperature, right? So there's more kinetic energy. They're still not moving relative to each other, but there's a lot more movement. If you get enough of that movement, you can break the forces that are holding the particles together and the thing will melt. So these intermolecular forces come from interactions between charges, partial charges, and temporary charges on the particles. And this is why we talk about intermolecular forces after we talk about molecular structure and polarity of molecules, because we need to understand that so that we can understand these intermolecular forces. So Coulomb's law is shown here. This is the whole thing. You don't need to memorize that. The important part of Coulomb's law is that the potential energy of two charged particles is proportional to the product of their charges divided by the distance between them. So if these charges are the same, this energy is positive, meaning the particles are going to be repelled, pushed away from each other. If the charges are opposite, one positive, one negative, this potential energy is negative, and so as the particles come together, their energy decreases, and that is a spontaneous process. They're attracted to each other. The larger the charges, the greater the attraction, and the distance is inversely related. And so the larger the distance between the two particles, the lower the energy. The larger the distance, the less the attraction. And so if we think about our life experiences with magnets, we can make some sense out of this. So if you imagine putting a magnet on the refrigerator, it sticks up there just fine. And then you've got a note from school or something, and you stick that up there and you put the magnet on there, and the magnet holds the piece of paper to the refrigerator, right? So the magnet and the refrigerator are like the oppositely charged particles that are attracted to each other. The thickness of the paper is the separation between them. If you add another piece of paper, probably still going to stick, but if you keep adding one piece of paper at a time, eventually, depending on how strong the magnet is, you'll get to a situation where the magnet sticks, but it can no longer hold the pages up, and they begin to slide down the refrigerator, right? You are at home now, and so you can go try this later if you want to. So why does it slide? Because R, the distance between the magnet and the refrigerator, is increasing. It's not increasing very much. The difference in the thickness of one piece of paper can cause it to not hold, right? So the distance between the particles is very important. The charge on the particles is also very important. So bonding forces are different than intermolecular forces. So here we have a water molecule. The bonding forces, which we've talked about probably more than you wished we would talk about them, are between the hydrogen atom and the oxygen atom. It involves the overlap of half-filled orbitals, and we have attraction between the negatively charged electrons and the positively charged nuclei. And this happens over a very close distance. For an oxygen-hydrogen bond in water, it's about 96 picometers. Intermolecular forces occur over a larger distance. So they happen between molecules, and so the distance between molecules might be 300 picometers, so 3 times the distance. That means that the forces are going to be much lower. We also have smaller charges because now we're not looking at the electrons versus the nuclei of each of these. We're looking at the overall partial charge of this molecule, or of one end of this molecule, and the partial charge of another molecule. So the distance is greater, the charges are smaller, the intermolecular forces are much weaker than chemical bonds. Any questions yet? So what are these forces? Well, dispersion force is the first one mentioned in the book. This one goes by some other names, sometimes called London forces, or London dispersion forces, Van der Waals forces, named after a person. My personal favorite is induced dipole forces. But the term that the author of the book uses mostly is dispersion force, and so I'll try to use that one to be consistent. So what are these dispersion forces? These are a result of fluctuations in electron distributions within molecules and atoms. So here we have an illustration of the same molecule at 3 different times. The nuclei is sitting there and being nicely predictable. And the electrons, as we have learned, are kind of squirrely, right? They're hard to pin down. They're particles and they're waves at the same time, and so they're kind of mysterious, and it's hard to say, where they are. You can pinpoint the location of an electron, but then you can't know its direction or its velocity. If you know the direction and velocity, then you don't know where it is. So if we took a picture of the molecule, we could identify, okay, right now the electron is here and here. And then maybe a couple seconds later, we take another picture, and now we see that the electrons are here and here. And a third picture might reveal that the electrons are both on this side of the nucleus now. They are not, at any given instant, evenly distributed. Overall, they are evenly distributed. If we took 1 million of these pictures, we would get 2 million dots, and they would form a spherical shape. But at any given instant, they can be lopsided. So if both of the electrons in this atom are on one side of the nucleus, that's going to cause an imbalance in the charge, because we have all the negative charges on this side, and we have this positive nucleus exposed on the other side. And so just like with polar bonds, where there's an unequal sharing of electrons, we can end up with a polar atom or a polar molecule. Now this atom is not going to stay this way. The next frame would probably show the electrons more evenly scattered about again. And so this is a very, very brief uneven distribution of electrons, but it causes one side of the atom to be partially negative and one side to be partially positive. Any questions? When my husband and I were on our honeymoon, we spent a couple days in San Francisco, and we took one of those blue and white cruises on the San Francisco Bay. Really, really pretty fun. So if you imagine this like a boat, and the electrons are the people on deck, right? This is a pleasure cruise, and you're going out in the bay, and the people are just kind of milling about, seeing the sights, and then, but sometimes you might end up with all the people on one side. That could happen randomly, but that could also happen because you're going past something that's interesting and attracts the people to that side. So we can get that instantaneous dipole in one atom, and that can induce or cause a dipole in a neighboring atom. So this boat now is going past Alcatraz, and the people all flock to one side of the atom of the boat to see Alcatraz. Or maybe this is a boat where everybody was looking at Alcatraz, and now it's listing to one side, and so this boat, everybody's looking because they're like, is the boat going to capsize? Are they going to tip over? It's kind of exciting. And then that causes this boat to tip, and then this boat over here sees that and wants to look as well. So we have a spontaneous, instantaneous dipole occurring, just randomness, but that causes or induces a dipole in a neighboring atom. So now we have this partial negative charge on one side of this atom, partial positive and partial negative, and those are going to attract each other. And over here, positive and negative, those are going to attract each other. So those attractions are instantaneous, they're very, very temporary. They come and they go, but they happen a lot. And so this is the force of attraction known as a dispersion force. I like induced dipoles because it is the attraction between dipoles that have been induced by one being out of balance. So how large is a dispersion force? Well, that varies. One of the things that affects the magnitude is how easily are those electrons polarizable? How easily do they move one side to the other? How easy is it to get them lopsided? In a larger atom, in a larger electron cloud, it's easier for that to get lopsided because the electrons are farther from the nucleus and they're held less tightly than the nucleus. So if we look here at these different noble gases, here's xenon. The nucleus is very small, but xenon is much larger than helium, and the electrons on the outside are quite far away compared to helium from the nucleus, and so they're not held as tightly. I think of xenon as being kind of a big flabby atom, right? And so, like a jelly or something, and so the electron cloud can get shifted around quite easily. Whereas helium only has 2 electrons, and those are held quite tightly to the nucleus, and so those are much harder to shift around. Another analogy I have for this is family size. So this is a family, let's just say one mom, and maybe she has one child, right? And I talk about this with other things as well, but when you have one child, it's much easier to keep track of them, right? To know where they are, say, in the house, or if you go like to the big Fresno Fair or something, you can keep an eye on that one child. If you have 6 or 500,000 children, then it's a lot harder to keep track of them, right? And so it's easier for all of them to get, off to one side or the other. So the easier it is for these electrons to get lopsided, the stronger the intermolecular force, the dispersion force. And so what we see here is as the molar mass of these atoms increases, the boiling point also increases. And the boiling point gives us a measure of the intermolecular force because helium will boil at 4.2 Kelvin, which is just a smidge above absolute zero. It's really hard to make liquid helium. And as we see larger and larger atoms in this family, we see the boiling point goes up. And so for xenon, we have to get up to the huge sum of 165 Kelvin, still incredibly cold. 165 Kelvin in order for this to boil. So this requires more kinetic energy in order to get these atoms to separate from each other and go from a liquid to a gas state. Stronger intermolecular forces hold them together, and so the boiling point is higher. So we have a general trend that the dispersion force increases with molar mass. If we're talking about molecules, the size of the molecule matters, but the shape also matters. So here we can look at two different isomers of pentane. So these have exactly the same molar mass, 72.15, because they have the same number of carbon and hydrogen atoms, but they're arranged in a little bit different way. So N-pentane, we have a long chain of carbon atoms, and in neopentane, we have a central carbon atom and the other carbon atoms are clustered about. And so this causes a difference in the shape of the molecule. So these molecules are more like a capsule shape. They're more elongated, and these molecules are more spherical. And so if you imagine these as objects covered with Velcro, you can see that these molecules, these two, can share a larger amount of surface area, and the larger the surface area of the Velcro, the stronger it sticks, right? I've never done it, but I should because I talk about it all the time. But I've seen those, bounce house inflatable things where you put on a Velcro suit and you jump and then you throw yourself at this Velcro wall, right? And you stick. It's like Velcro holding a person off the ground, and yet you may have a pair of shoes with Velcro flap where that stupid little flap will not stay down, right? Well, if you have a small area for interaction, the force of attraction is going to be much weaker than if you have a large area of interaction. So we see a difference in the boiling points. Neopentane, the spherical one with small area for interaction, boils at 9.5 degrees Celsius. N-pentane boils at 36. Because of its shape, there's much stronger interaction between the molecules. Anybody have any questions? Here's a chart showing this relationship with some straight chain alkanes. So here we have pentane, 5 carbons, hexane, 6, 7, 8, 9. And so these are all straight chains, so we're not looking at the effect of shape here, but we're looking at the effect of molar mass, so how easy is it for them to polarize. And because of the shape here, nonane is much longer and has more surface area where the two molecules can attract each other. So this is a combined increase in polarizability and increase in surface area, and we see that the boiling point of these changes dramatically from pentane, which is a gas at room temperature, up to nonane, which is definitely a liquid. So this will not boil until 140 degrees Celsius. So here's a question. Which halogen has the highest boiling point? The halogens are diatomic molecules. We've got chlorine, bromine, and iodine. Which one is going to have the highest boiling point?
Say iodine.
Yeah, it's going to be iodine. It's going to be iodine because iodine is larger, right? Iodine atoms are larger, so the iodine molecule is going to be larger. The electrons are more easily polarized, and so the intermolecular forces of the dispersion force is going to be stronger, and so it requires a higher temperature to get it to boil. The next type of force is called the Dipole-Dipole Force, and as the name suggests, this is an interaction between two dipoles. I didn't emphasize it earlier, but dispersion forces are present in everything. All atoms, all molecules, dispersion forces are present. Dipole-dipole forces exist in molecules that are polar. So if you have a nonpolar molecule, no dipole-dipole force, but anything that's polar, you will. It's the same type of interaction. It's an attraction between a partial negative and a partial positive charge. The difference here is that in polar molecules, that charge imbalance is permanent. The molecule has a permanent dipole. In this molecule, this oxygen end is always a little bit negative. The hydrogen side is always a little bit positive. The reason for that is the higher electronegativity of oxygen. And so in these bonds, the oxygen hogs the electrons, right? It takes more of the electrons, pulls more of the electrons over here. So this side is negative, that side's positive. So you have one of these molecules and another molecule. The positive side of one will be attracted to the negative side of the other. And that is the dipole-dipole force. The type of attraction is exactly the same. What's different is that these dipoles are permanent, they're always there, instead of just coming and going instantaneously and randomly. We can also look at an electrostatic potential map where we see more electrons here, and those are going to be attracted to this side, which is deficient in electrons. So all molecules have dispersion forces. Polar molecules have dipole-dipole forces in addition to the dispersion forces. And so we see if we compare polar molecules with nonpolar molecules, that the polar molecules are going to have a higher boiling point. So here we're going to compare formaldehyde and ethane. Their molar masses are almost identical, and that's important because we don't want to be looking at a difference in dispersion forces. So same molar mass, the dispersion forces should be pretty similar. This molecule is polar, this one is not. And this is where that sort of shortcut method that I told you about can help you, because we need to be able to identify polar molecules versus nonpolar. So my shortcut method, looking at these Lewis structures here, I'd ask myself, well, are there any lone pairs? There are no lone pairs, so the first condition is met. But are all of these atoms the same that are bonded to the carbon? No, they're not. The oxygen is different. And so that tells me that this is a polar molecule. It's lopsided. Here we have two carbons in the middle. There's no lone pairs anywhere. And when we look at all of the atoms bonded to those carbons, they're all the same. And so this is a nonpolar molecule. Another thing that you should remember is that carbon-hydrogen bonds are nonpolar. And so these carbon-hydrogen bonds, the electronegativity difference is small enough that those are considered nonpolar. And so all of the bonds are nonpolar, so there's no way you can have a polar molecule. Here, these carbon-hydrogen bonds are nonpolar, but carbon and oxygen are definitely different, and this is a polar bond right here. So what we see is a big difference in boiling point and melting point. The formaldehyde, which is polar, has higher boiling and melting points than the ethane. Ethane boils at minus 88. Formaldehyde boils at minus 19. So this is higher. Melting point minus 183 versus minus 92. This is a bar chart showing boiling point versus dipole moment. So the dipole moment, measured in debye's, is a quantitative measure of the dipole present in a molecule. We kind of talked about it, but we didn't really do anything with it. But here we can see we have 5 different compounds with very similar molar masses, all about, mid-40s, mid to low 40s. But their boiling points are different. Here we've got, around 225, and this one's up around 350. So it's not the dispersion force that's causing this difference. It's the dipole moment of these molecules. Acetonitrile is much more polar than propane. Propane is really nonpolar. There's really no dipole-dipole forces. As we go here, the dipole-dipole force strength increases and the boiling point increases. Polarity of molecules is also very important in determining solubility. Miscibility, that's a weird word. This is not a word, but might help you remember what miscible means. Mixable, miscible. That's basically what it means. So miscibility, mixability. Are 2 liquids mixable? Well, the little catchphrase we have is like dissolves like. So if you have 2 polar liquids, they will probably be miscible. They'll probably mix together just fine. If you have 2 nonpolar liquids, they'll probably mix together as well. But if you have a polar and a nonpolar, they will not mix together. We see that with oil and water. The illustration here is with pentane and water. These are nonpolar molecules. They're held together by just dispersion forces. The water has dispersion forces in addition to dipole-dipole forces. And so these water molecules are attracted to each other very strongly, much more strongly than they are to the pentane, or that the pentane are to each other. And so essentially the water molecules are trying to crowd together because they like each other so much, and they're just going to exclude the pentane. They're going to squeeze it out. The pentane being on top is just because its density is less. There are other polar-nonpolar mixtures where the nonpolar substance will go to the bottom because it's more dense. So this is something we should be able to do. Identify which of these molecules have dipole-dipole forces. So what we're looking for here is the molecule polar or not? So that first one is Ci4, and I wrote the name out there, carbon tetraiodide, because I don't want us to think that this is 4 chlorine atoms bonded together. So we really should look at the Lewis structures for these. So for this first one, 4 iodines around the carbon, and then you'll get lone pairs out here. I'm just going to do these real fast because the point here is not to review Lewis structures. So looking at this Lewis structure, is this molecule polar or nonpolar? Are there any lone pairs on the central atom? No.
No, it's not.
So it's nonpolar. We've got no lone pairs, and all the atoms bonded to the central atom are the same. This is a symmetrical molecule. When we have lone pairs, it gets lopsided and it's polar. If we have one or more of these atoms that are different from the others, it's also going to be lopsided and most likely polar. So this is a nonpolar molecule. Does this have dipole-dipole forces? This means yes, and this means no. Do nonpolar molecules have dipole-dipole forces? Dipole-dipole forces are between polar molecules. So if the molecule's nonpolar, it's not going to have dipole-dipole forces. So this does not have dipole-dipole forces. Let's look at this one, CH3Cl. So carbon in the middle, 3 hydrogens, and a chlorine. The chlorine's going to have lone pairs on it. Are there any lone pairs on the carbon? No. So that's condition 1. Are all of these atoms the same or have the same electronegativity? No, they don't. So in order for it to be nonpolar, we have to have both of those conditions met. So this is a polar molecule. Do polar molecules have dipole-dipole forces? Yes, they do. So this one is a yes for the dipole-dipole force. How about HCl? Well, this is a much simpler molecule, right? It's just 2 atoms. And so then we can look at our shortcut. Well, are there any lone pairs on the central atom? And you can say, well, there's no central atom because there's 2. Which one's central? When we have 2 atoms, we have a single bond. There's only one bond. And so the polarity of this molecule depends on the polarity of the bond. Is this bond polar? Sorry, I'm hearing weird noises behind me. Is this bond polar? Well, how do we determine that without pulling out a table and looking up electronegativities? Most of the time, if you've got 2 different elements, bonded, it's usually polar. There are exceptions, but we probably won't run into those on a test for sure. So these are different, and so I'm going to predict that this is a polar molecule. Since it's polar, it has dipole-dipole forces. If you have 2 identical elements, then obviously they have to have the same electronegativity. It's going to be nonpolar. The other one that you should remember is carbon-hydrogen. So if we looked at like chlorine, Cl2, these atoms are the same. And so there's no difference in how attractive they are to the electrons. And so this is going to be a nonpolar bond. The molecule will be nonpolar. Something like this, where we have 2 different elements, most of the time that's going to be a polar molecule. Any questions? Being able to predict the polarity of a molecule and the types of intermolecular forces that are present and their relative strengths is really important for organic chemistry. It gets used a lot. Here's another conceptual question. An electrostatic potential map for acetonitrile, which is polar, is shown here. So here we see from the coloration that we have more electron density here and less over here. From this map, determine the geometry for how two acetonitrile molecules would interact with each other. Which of the orientations shown to the right is the most likely? And then over here, we have different possibilities of how these two molecules could be attracted to each other. So let me make this one look a little more like these. What we've got here is the carbon with the hydrogens and another carbon and then the nitrogen over here. So this is the nitrogen end, this is slightly negative, and this end is slightly positive. So how would two molecules like that interact with each other with the maximum attraction? A, B, C, or D? Or we could go with 1, 2, 3, or 4, and you could hold up fingers.
Sorry, I didn't hear the question.
So, looking at this molecule, we're wanting to know which of these combinations would best describe the interaction where they would be attracted to each other. So we're looking at positive ends and negative ends, and how would they attract each other? Whoops. So if you think about magnets, and one end is the North Pole and the other end is the South Pole. So down here we have two North Poles together. Okay, so I've got an answer of B. Let's look at B. So here we have the partial positive and the negative end kind of next to each other here and here, but then these negative parts are also kind of close together. So this is probably the second best one. This is exactly the opposite of what would happen. We're not going to have the two negatives attracted to each other. These are going to repel. So we've decided it's not D. B is not quite good enough. A, yeah. So in this arrangement, we have the negative end next to the positive end. So this is like magnets lined up like this. Whereas B would be the magnets like this. And so the negatives here are going to push each other away. This one at the bottom, we have both North Poles together. That's not going to be attractive at all. And here we've got one sideways to the other. You guys have any questions about that? Does that make sense? Polar molecules act much like magnets, and they will line up relative to each other and they will be attracted to each other. The third intermolecular force is called hydrogen bonding. Hydrogen bonding really is a dipole-dipole force, but it's extra strong. So we could call it super dipole-dipole force. It's found in polar molecules, but only certain polar molecules, ones that have hydrogen bonded to fluorine, oxygen, or nitrogen. And these are significant because they are small atoms and they are highly electronegative. So we get stronger partial charges, larger partial charges, so stronger forces, and the small atoms allow these molecules to get close to each other, and so shorter distance also gives stronger interaction. So here we have something like HF, and so we have the negative attracted to the positive end of the next one. So it's the same arrangement, it's the same idea as dipole-dipole force. The difference is that these partial charges are larger and the atoms are smaller so they can get close together. So how do we remember what we need for hydrogen bonding? Do you guys see the movie E.T.? If you haven't, you should watch it. It's a classic. E.T. was this alien, and he would point at the sky, and what did he say? E.T. phone home, right? He'd point, E.T. phone home. Phone home. F-O-N-H, right? Phone home. So if you have fluorine, oxygen, or nitrogen bonded to hydrogen, it's going to have hydrogen bonding. So here we're looking at hydrogen bonding in ethanol and hydrogen bonding in water. I'm going to do water first. So here are structures for water, and it has a bent structure, and so it's a polar molecule. We have oxygen on this end and hydrogen on that end. We have an oxygen-hydrogen bond. So we need fluorine to hydrogen, oxygen to hydrogen, or nitrogen to hydrogen. The hydrogen bond is, where did that come from? I don't know where that came from. The hydrogen bond is the attraction between the molecules. The bond between oxygen and hydrogen is a bond involving a hydrogen atom, but that is not a hydrogen bond. A hydrogen bond is an extra strong dipole-dipole force. It is not a covalent bond. Here we have ethanol. Ethanol has an oxygen-hydrogen bond. So that is the bond that tells us that this is going to have an especially high dipole moment. It's going to be extra polar, and the size of these atoms allows the hydrogen to get closer to the oxygen, and so this is also going to have hydrogen bonding. So very important to understand that hydrogen bonds are between molecules. They're not within a given molecule. Chemical bonds are between the atoms inside of a molecule. Chemical bonds are much, much stronger. This actually should probably be after that point instead of here. Hydrogen bonds are 2 to 5% as strong as a covalent bond. So although they are a very strong intermolecular force, they are much weaker than covalent bonds. In this table, we're comparing ethanol and dimethyl ether. And both of these molecules are polar. Might not be obvious about that one down there, but if we draw the Lewis structure, the oxygen in the middle, there are lone pairs on the central atom. So this actually has a bent structure, and this side of the molecule is going to be a little bit negative relative to that side. So this is a polar molecule. Ethanol, also a polar molecule. And in fact, their molar masses are identical because they have the same number of carbons and hydrogens and oxygens, just arranged differently. So if we look at ethanol, now looking at this, just following the rules strictly, the central atom, no lone pairs, everything bonded to the central atom, is it the same? No, it's not, because we've got oxygen here and we've got hydrogen and carbon over there. Another thing you can do is you can look at this molecule and you can ask yourself, well, does it look symmetrical or does it look lopsided? And this one's definitely lopsided. This one is symmetrical, but with the lone pairs here, it is going to be somewhat polar. Ethanol has this oxygen-hydrogen bond. That's the phone home. We've got oxygen-hydrogen bond. In dimethyl ether, we have hydrogens and we have oxygen, but the oxygen is not bonded directly to a hydrogen. And so this does not qualify for hydrogen bonds and doesn't have hydrogen bonds. So, this one on top has hydrogen bonding. It's got dipole-dipole forces because it's polar, and it has dispersion forces. Everything has dispersion forces. The one on the bottom is polar, so it does have dipole-dipole forces. It also has dispersion forces, but it does not have hydrogen bonding. I don't know how that happened. So, stronger intermolecular forces here, higher boiling point and melting point. Ethanol boils at 78 Celsius, dimethyl ether boils at minus 22. And the difference in these boiling points is due to the strength of the intermolecular forces. Stronger intermolecular forces, you have to get to a higher temperature, a higher kinetic energy for them to break loose from each other. We also see the same trend with the melting points. Because water has hydrogen bonding, it has some rather extreme properties. This is a graph showing boiling point versus molar mass, and we have group 4A elements bonded to hydrogen and group 6A elements bonded to hydrogen. And we see that there's a trend here. So these ones on the bottom, the carbon drops off a little bit, but there's a pretty good trend here. And then for the group 6A, these three make a very nice trend, but then water is way off from where it should be. We would predict that water would be more around here, but it's not, it's way up here. The group 6A compounds are all polar, and that's why their boiling points are higher than the group 4A, which are pretty non-polar. But what's happening here with water is that water has hydrogen bonding. None of these other compounds fits the ET phone home, FON, bonded to hydrogen, except for water. because water has hydrogen bonding, it has much stronger forces holding it together, and so its boiling point is much, much higher than the rest of these. If it weren't for hydrogen bonding, there would be no liquid water on Earth and there would be no life. So here's a question we should be able to answer. Which has the higher boiling point, HF or HCl, and why? So if we're looking for higher boiling point, we're looking for stronger intermolecular forces. And so we look at these two molecules. Are they polar or nonpolar? They're each just two atoms. Are these two atoms the same or different? They're different, right? Hydrogen and fluorine versus hydrogen and chlorine. So if you don't have a table of electronegativities to look at, I expect you to assume that their electronegativities are different and that these are polar molecules, right? And our general trend of electronegativity is fluorine's over here, and electronegativity gets stronger as you get closer to fluorine. And so they're fluorine and chlorine's right here, and so fluorine is more electronegative than chlorine, but hydrogen's over here, right? So these are going to be polar molecules. There's some size difference, right? So fluorine's smaller, and so the lower molar mass here would tell us the dispersion forces are less, but dispersion forces are the weakest. And so if we're looking at dipole-dipole forces, those are going to be stronger and mostly outweigh the effect of the dipole forces. But there's another important difference here. What does HF have that HCl does not?
The phone home.
The phone home, yep, hydrogen bonding. So here we have
the hydrogen bond.
Yeah, because of the phone home, we've got hydrogen bonding. It also has dipole-dipole and dispersion. But HCl, no hydrogen bonding, it just has dipole-dipole and dispersion. Hydrogen bonding is the strongest of the intermolecular forces, and so because this one has stronger intermolecular forces, what does that mean about the boiling point? Is this boiling point going to be higher or lower than HCl? The way I think about this is you've got these two things, and if they're really, really stuck together, if they have strong intermolecular forces, you have to get to a higher temperature, much more energy to pull them apart. If they're just stuck together a little bit, very weak Velcro, they're going to come apart at a much lower temperature. We have less energy required. So stronger attraction between them is higher boiling point. So the HF has higher boiling point because it has hydrogen bonding and the HCl does not. Does that make sense? The last intermolecular force, which I understand why they put it here, and yet it's not really an intermolecular force, is the ion dipole force. And as the name suggests, this happens between an ion on one substance and a dipole on another. And so this mostly happens when we have ionic compounds mixed with polar compounds, especially water. So this is really important in aqueous solutions of ionic compounds, which we deal with a lot, so this is important. And this force is stronger than hydrogen bonding. It's responsible for the ability of ionic substances to form solutions with water. So what happens here is we've got sodium chloride dissolved in water. Here's our chloride ion. And so here's the ion in the ion dipole force. And then we have the water molecules that are polar. And so this negative ion is attracted to the positive side of the water molecule. And that is the ion dipole force. It also works with a cation like sodium because the negative side of water is attracted to the positive cation. And so we also have an ion dipole force here. The reason I don't like this listed as an intermolecular force is because this is not between molecules. It's between a molecule and an ion. And all of the other intermolecular forces occur within a pure substance. So hydrogen bonding occurs in pure water. Ion dipole forces can only happen in a mixture. So I think that's kind of iffy, but it's here and it is important. And then this is a table that summarizes these different intermolecular forces. So it's important to know the basics of what these forces are. They are all attractions between opposite charges, but the source of that charge varies. We should know their relative strength. Dispersion is the weakest, and they increase as we go down here. We should know what sorts of things these are present in. Everything has dispersion forces. Polar molecules have dipole-dipole forces. If we've got fluorine, oxygen, or nitrogen bonded to hydrogen, phone home, we can have hydrogen bonding. And here, mixtures of ionic compounds and polar compounds. And we do have an asterisk here. This is a general trend in strength, but the dispersion force can be very strong for molecules of high molar mass. And so this is just generalizations. But based on identifying what type of forces compounds have, we should be able to predict which one has a higher melting point, lower boiling point, etc. We should also be able to predict which things might mix together. So here's an example of a question like that. Which substance has the highest boiling point? Just without drawing Lewis structures or anything, can you identify something here that's nonpolar?
The N2.
Yeah, N2 is nonpolar because two identical nitrogen atoms. So if this is a nonpolar molecule, is it going to have strong intermolecular forces or weak? It only has dispersion forces, right? Because that's what everything has. It's nonpolar, so it can't have ion dipole, dipole-dipole, or hydrogen bonding. So very weak forces. CO, polar or nonpolar? Two different atoms.
Should be polar.
Should be polar. Yep. Like I mentioned, looking at two different nonmetals, there are combinations that are nonpolar, but I expect you to guess that it's polar if you don't have other information provided. So this is polar. What's the strongest intermolecular force that this compound has? It has dispersion forces, but it has something stronger as well. Dipole-dipole forces? This can't have hydrogen bonding because it has no hydrogen, right? If there's no hydrogen, there's absolutely no hydrogen bonding. So these forces are stronger than the dispersion force. And then let's look at this one. Does that look symmetrical or lopsided?
Lopsided.
It looks lopsided. So that one looks polar. And we can look at the Lewis structure and kind of confirm that. Those electrons are green. Carbon-hydrogen bonds are nonpolar, so this is all nonpolar here. Here we've got an oxygen with lone pairs on it, and so this is definitely going to be a polar molecule. So polar molecule is going to have dipole-dipole forces. Oops. Does this meet the criteria for hydrogen bonding? Phone home.
I think so.
Yeah, we have an oxygen directly bonded to hydrogen. So for hydrogen bonding, we're looking at a fluorine hydrogen bond, an oxygen hydrogen bond, or a nitrogen hydrogen bond. So it's got this one. So this one has dipole-dipole forces plus hydrogen bonding. So are the intermolecular forces here going to be stronger than carbon monoxide or weaker? We've got dipole-dipole forces in both of these, and then this one has additionally hydrogen bonding. So this one has the strongest forces. If we're looking for highest boiling point, we're looking for the one where we need the most kinetic energy in order to break it apart. So that's going to be the one with the strongest forces holding it together. So which one has the highest boiling point, A, B, or C? Thank you, A.